we are covering axial stress and strain, Hooke's law, and Poisson's ratio, all critical topics within the mechanics of materials section for the FE civil exam. Let's start with the foundational concept of axial stress, which the NCES Reference Handbook defines as sigma equals P over A. This represents the internal force P acting perpendicular to the cross-sectional area A. On the exam, you'll see problems involving a simple tension or compression member, like a steel rod or a concrete column. A common trap is a unit mismatch. If the load is given in kips and the area in square inches, your stress will be in kips per square inch, or KSI. If the problem provides the modulus of elasticity in PSI, you must convert your units to be consistent before proceeding. Next is axial strain, represented by epsilon, which is the change in length, delta, divided by the original length, L. Strain is a dimensionless quantity, often expressed as inches per inch or millimeters per millimeter. The exam will test your understanding of the difference between deformation, which is the absolute change in length, and strain, which is the normalized ratio. A question might give you the material properties and ask for the final length of a member after loading, requiring you to first calculate the strain, then the deformation, and finally add or subtract it from the original length. These two concepts are linked by Hooke's law, which states that stress is proportional to strain within the elastic region. The formula is sigma equals E times epsilon, where E is the modulus of elasticity, or Young's modulus. This is a fundamental material property found in the handbook. For steel, it's commonly taken as 29,000 KSI, or 200 GPa. By substituting the formulas for stress and strain into Hooke's law, we derive the single most important formula in this section, the deformation formula, delta equals PL over AE. A memorable way to keep this straight is the acronym PLEA. Just remember delta equals PLEA, or PL over AE. A classic FE exam problem will provide most of these variables and ask for the missing one, but the trick is often buried in the units or the geometry of the cross-section. Now let's discuss Poisson's ratio, represented by the Greek letter nu. This describes how a material behaves in the directions perpendicular to the applied load. When you stretch a material, it gets longer, but it also gets thinner. Poisson's ratio is the negative of the ratio of this lateral strain to the axial strain. The formula is nu equals negative epsilon lateral divided by epsilon axial. The negative sign is a common point of confusion. It's there because a positive axial strain from tension causes a negative lateral strain, meaning the cross-section shrinks. An exam question might give you the axial load, material properties, and original diameter of a rod, and then ask for the final diameter. You would first calculate the axial stress, then the axial strain using Hooke's law, then use Poisson's ratio to find the lateral strain, and finally use the lateral strain to calculate the change in diameter. For most steels, this value is around 0.3. A final point is volumetric strain, which is simply the sum of the strains in the x, y, and z directions. For a simple uniaxial load in the x direction, the strains in the y and z directions would be equal and calculated using Poisson's ratio. The exam loves to test these interconnected concepts, so mastering the relationship between stress, strain, deformation, and the material properties E and nu is absolutely essential for passing. For free practice questions, AI-powered explanations, and more exam prep tools, visit openexamprep.com. That's openexamprep, all one word, .com.